Thank you everyone for joining today. Um, Today we have a very interesting module with an introduction to the EBRAINS research infrastructure. This module is the second module of the EduBrains program. Some of you who are participating today are formally enrolled in this program, which is funded by the Federal Ministry of Research and Technology and Space in Germany, but that is also heavily supported by the German national node of EBRAINS, and that works very tightly in collaboration with the whole EBRAINS research infrastructure. And some of you are not directly involved in this program, but just to give you an overview, this program aims to train a set of young researchers throughout a set of modules and to create a new generation of researchers with skills in both technology and neuroscience who can address questions, future questions for brain health using e-technologies. So we're very excited to be moving forward this program. And then this is a hybrid module. So both the formal members of the program as well as external participants can join and listen in. So thank you very much for taking the time to join us. Let me see if I can. Yes, okay. This is the agenda for today. We are gonna go a full day, so I hope you don't get tired of me. But I'm gonna try to make this as fun and interactive for you as possible. Well, to what extent can be done. We're going to start with a general introduction to eBrains, and then we're going to talk about what is, how can you do research on eBrains? What are your expectations about eBrains, and how to start getting acquainted with the infrastructure. Then we have a short coffee break, and we come back to look into one of the core services of eBrains, that's the data services. Then we take a short lunch break and we move into one of the longest sessions that has to do with simulation analysis and visualization tools. Then we move into the super exciting neuro-inspired technologies, high performance computing, and AI. We go for a quick coffee break before we come back to discuss collaboration tools within eBrains. And then we will have some questions and answers. In the middle of all of this, I have prepared for you some kind of treasure hunt. So I will share with you some questions, and you will have to go around and try to find out what are the answers to these questions. And at the end, they should form something coherent. At least I hope. A coherent message for you. Yes, so this is the plan. And the first thing that I want to say is that today I'm going to talk about many tools and a lots of work that has been done within the Human Brain Project and eBrains. And this is, of course, not my work directly. I have contributed to the development of some of these tools, but here I am basically showing you how to navigate the infrastructure that has been developed by hundreds, if not maybe thousands of researchers along Europe and with collaborations everywhere in the world. So definitely I in advance thank all my colleagues who have provided input, with whom I've discussed about this, and who also create and help create this beautiful environment that forms the eBrains research infrastructure. Okay, then without further ado, let's get started with what is eBrains. So eBrains is a digital research infrastructure that was designed to understand the brain. It should support neuroscience research, brain medicine, and the development of brain-inspired technologies. That means that in itself, eBrains is tremendously multidisciplinary. even if it doesn't look like it. So it is not only about doing simulations about the brain, it's everything that surrounds understanding how brains work. And this then turns into a very complex question or sets of questions that cannot be answered with a single tool. And this is why EBRAINS is not only a research infrastructure for itself, so it's more like a real ecosystem of collaborating researchers that put together a lot of effort to provide reusable and sustainable tools for you and for the rest of the world. EBRAINS has been developed within the Human Brain Project, which was the European flagship project that lasted about 10 years and a little bit more. And it was a large investment from the European Commission to create this infrastructure. It was an infrastructure project aimed at creating the tools to understand the brain. And now it's our task to make use of these tools to really advance all these different connected areas. EBRAINS is now part of the S3 roadmap, so the European Strategy Forum on Research Infrastructures. And this is important because it gives it a basis for sustainability and also support from the political and organizational layers of the European Union. And EBRAINS now is organized around a central hub, which coordinates a network of services that are provided through national nodes. And I mentioned before, this program, EduBrains, is supported by the German national node, but there are many different nodes. I will just show you in the next slide. And they collaborate together to provide these networks of services and tools that form the research infrastructure. The central hub is currently located in Brussels, and it is an international nonprofit association, which you will frequently hear as the EBRAINS AISBL. So it is the EBRAINS AISBL is the central hub, and the EBRAINS research infrastructure is a whole set of tools, services, and hardware and software infrastructure that is provided to you for your research. The national nodes are then put together and represented in a national node board. So they take decisions about how to move forward with the EBRAINS research infrastructure. And in the end, each national node has different members. We have about, I think, more than 50 associate members at the moment, 11 full members. And this, you can see here, a nice map that I took from the EBRAINS website, where you can see which countries are currently have institutions that are members of EBRAINS, and also the 11 current national nodes. As you see, the EBRAINS research infrastructure is a highly distributed collaborative effort to provide state-of-the-art tools for brain research. So more than more than or beyond the technology, the science, and the will to understand the brain, there is this strong bonding collaboration that makes EBRAINS a really strong research infrastructure. So some of the highlights, well, as I mentioned, it's very interdisciplinary and it's meant to do collaborative research. So this is also why we're going to look at the tools that allow you to collaborate with others to do your research. It is just obvious now that some of the questions that we have related to how the brain works cannot be answered neither by a single person nor in a single discipline. So we need to work together. and EBRAINS should help you achieve that goal. EBRAINS is also very focused on open, fair science, and that means that we have a set of community-tested tools, methods, curated data, and services. You don't have to start from scratch to try to understand how certain things in the brain work, or how to apply certain methods to develop new techniques to create new treatments for neurodegenerative diseases. We can provide via the EBRAINS research infrastructure already a basis that of course you can extend, of course you can reuse and integrate in other tools, but if it's already there, it's a nice advantage, and it also helps there's reproducibility and reusability because it's a community effort. And if one makes a mistake or oversees something or doesn't have time to integrate an interesting feature, maybe others have the effort and the time available to do this. So joining forces is the best strategy. And of course, this exchange of ideas among disciplines is really interesting and important. By interacting with each other, we start building a common language. We start identifying common elements that unite our efforts and our time. And this is the best way to collaborate and then come up with breaking research that can really help society get in the future. Now, EBRAINS is a highly interconnected digital environment. We will see today that EBRAINS is composed by so many tools and services. There are so many of them, and in these talks that I will have in the following hours, I will not be able to show you all of the tools that are available. I basically took a subset of them that I think are, in this case, important for your experience within the EduBrains program, but also because they are the most visible, mature, and useful in the more generic manner. But there are so many others, absolutely wonderful tools that get less attention, unfortunately. You will have the chance also to consult the website and get to know all of them if you want. So please don't think that this is the end. There will be a lot more to know and understand. But one of the key features of the EduBrains infrastructure is this interconnection. So thanks to the work that we had during the Human Brain Project, we also had the possibility to discuss a lot how we wanted to create this infrastructure and what would be the technical guidelines to make this true. And there is a lot of effort behind EBRAINS to have standards and to have validation and tests of the tools that we provide, and to enable these tools to work together. So if one produces some data, it should be possible that you take another tool and you can analyze that data, and you can take another tool and maybe integrate that data and create a model of how the cortex works, right? So this interconnection is not always easy to see from the single tool perspective, but I'm going to show you a few examples throughout the day that I hope give you some inspiration. And if you identify that there is something that you would like to have connected, reach out, and we will see if this is already possible or is something that we should work on. As said, the EBRAINS research infrastructure is a community project as well. So we need you and your requests to understand what is missing and where to move forward. We have built the infrastructure in such a way that it's flexible. and you can easily integrate new tools and services. That being said, we have set also a minimum level of, let's say, technical maturity for the tools in order to ensure that these tools will be reused and that provide minimal level of validated outputs to the end users. So if you develop a new tool or want to provide a new service in the future, you will have to go through some checklists to make sure that your tools and services fit the technical requirements and can also automatically be tested and integrated into the infrastructure. EBRAINS really translates what was years of investment from Europe into projects like the Human Brain Project and now EBRAINS 2.0 into benefits for society. And one of the ways in which it does that is by training the new generation of researchers, among which you are part of. And some of you who are joining us today, especially all the participants in the EduBrains program. And we are actively trying to integrate these tools and services into European universities and also more programs so that more people can make use of this great environment for brain research. Okay? So you probably have seen the new website of the EBRAINS research infrastructure. And this is, let's say, the first step into getting to know the tool environment. But of course, the first thing you have to do is to get an account. I know that everybody in EduBrains already and the formal participants of the program have an account. If other people listening today, you still don't have an account, please register. It's free. And this is the first step to start using the EBRAINS ecosystem. Of course, it is important that you use your institutional email addresses. And this is because this allows us to validate that you come from an institution that we had already authenticated and validated that exists, and it's to maintain and to ensure security within the platform. This account that you got is the key to move inside of the EBRAINS research infrastructure. So basically, I would say 99% of all the services in EBRAINS work by gathering your identity from your account and authenticating you through that account, but also identifying if you have the right authorization to access different levels of the services and tools. So this unification across the EBRAINS research infrastructures through its authentication and authorization infrastructure is a key technical element that allows you to have a single key to open all the tools in the infrastructure. Another important thing, support. When you don't know where to start, if you have a problem, if you have any type of technical problem, from the most basic things like I got a 404 error in one of my services for some reason, I don't know what is going on. I need to ask somebody, all the way to I have a great idea to do research and I don't know how to get started. All the questions from there, from one stream to the other, and in the middle, you can ask us via our support infrastructure. You can go to the website and contact us, fill in the support form, and we will be glad to help you. We have a high-level support team that allows us to observe how the more general questions, but we also have the basic support. And the support is divided in different layers depending on the complexity and the scope of your questions. But I really, really, really recommend that you contact us if you have really any question that has to do with how to use the infrastructure, or I got a problem with it. Okay, great. Um, there is also a private space for each of you in the EBRAINS website. You can log in. So there is in the top right section of the website a way to log in. You can log in with your EBRAINS account, of course, and you will get an overview and a dashboard where you will find the things with which you have been interacting in the past. This section is still being developed further, but the idea is that here you have a small space for you where you have a better overview of what is going on centrally with your eBrains services and access. Okay, very good. So this is probably an old version of the architecture of the eBrains research infrastructure. But yeah, it's the one that I had at hand, and things have evolved slightly from here, but not radically too much. The important thing is that we have different layers of services that run behind the scenes, and some others that are more user visible. We have a front end that combines collaborative work environments. We are going to look at them towards the end of the day. We have these dashboards, for example, that I just showed you, where you can have your personal working space. We have data visualization tools, for example, the Zebra Explorer that allows you to navigate the atlases, and we will look into that. Then in the middle, we have the set of eBrain services. This is what we will mostly explore today in terms of simulation, analysis, and visualization as well, data analytics. And below that, there is a layer of platform middleware. This is what makes eBrains work together and orchestrate in the background things like, for example, managing your authentication, but also making sure that tools are constantly being tested, integrated, and deployed to the different sets of infrastructure front-end elements or environments that we have. And so it is a very important layer to keep the cohesive, unified feel of the infrastructure. In the lowest layer, we have the infrastructure itself, so where things are running, the supercomputers, the computers, the neuromorphic hardware, the actual deployment in virtual machines or interactive computing services, the data repositories, everything that is more hardware related, and the immediate thin software layer that should be used on top of them. On the lateral side, we of course have the vertical alignment to very important topics in innovation, education, partnering with other projects, because eBrains being so large, of course, also touches many other projects emerging at the European level. So it is really spreading laterally to different initiatives, even worldwide. And of course, there is the operations and administration, which makes sure that the operations of the infrastructure are actually done, have to do with the security, with auditing, with accounting, and some of the more managerial administrative tasks. So as you see, the infrastructure itself is very complicated, and you probably will basically interact only with the first two layers, the front end and the eBrain services. If you start being more into the deployment of new tools, of new services, you may also have to interact with the platform middleware. But in general, um, I thought it was important that you also looked behind the scenes to see what is being thought behind the organization of the infrastructure. And now I'm gonna very quickly give you a super fast in like taste of the different sections that we will go deeper into in the next hours. So I mentioned the data services. There are a large amount of data services in eBrains. We have to do with data from many different modalities that have to do with totally different scales, both in terms of space and time, of how the brain, of the state of the brain, of both of the structural and functional features of the brain. So data is one of the most fundamental elements of the infrastructure, allowing you to utilize data, to navigate data, to share data, to create your own outputs and share them with everybody in an interactive and novel way. So for that, we have, for example, the knowledge graph, where you can add data sets. We have the data sets, but also models, software, anything that you want people to be able to find. We have the live papers, where you can have your own manuscripts and then use this platform to have more interactive exchanges with the readers of your manuscript by providing interactive access to your data. We have, of course, the atlases that really provide a unique source of insight into the structure of the brain, and in the future also of the function, also anchored to the same space of these data structures. And the collaboratory, where you can share information with others and create your projects and work together to solve your scientific questions. We also have a variety of simulation tools that go from the molecular subcellular level all the way to the whole brain level. In time and space, they cover most of the features that we are aware are important for the brain. And this allows you to create models of how these features work, mathematical models, but also we have tools that allow you to analyze the outputs, integrate the data, and so on. Of course, a key feature of eBrains is that you can connect those data services with these simulation and modeling services in order to create even more powerful hypotheses or yes, digital playgrounds, so you can explore what happens in different scenarios. We, of course, have a variety of visualization and analysis tools that have to do with observing the dynamics, but also just exploring the structure of a specific model, and or observing how experimental data looks like and trying to extract important features from it. So we have many different tools for this. We, of course, have the high performance computing, neuromorphic hardware tools, and we also have a set of curated workflows that interconnect all of these things. And we are working more and more into developing such workflows so you can reuse them, extend them, utilize them better. But in the end, the idea is that you can connect your atlases, connect your modeling, connect your compute, generate your hypotheses, do scientific validation, and start all over, reutilizing the eBrains platform to ensure that you have correctness, that there is just that your workflows are usable, reproducible, that you can ensure a specific level of quality outputs from your research. And in the end, you also can have features that monitor how these outputs are being generated and produced, and produce metrics out of them. Here I'm also mentioning another research infrastructure called Phoenix. Phoenix was emerged together from the fire, together with the Human Brain Project, and connected the largest high-performance computing centers in Europe to provide a basis for answering these questions in digital spaces, right? So to provide access to high performance computing, to cloud resources, to storage. Today, Phoenix is changing. It's slightly different from what it was, but the members that were part of Phoenix originally still strongly support the EBRAINS research infrastructure and contribute to its success and its future sustainability. And we are now coming to the final section of this small part. I know I'm taking a bit more time than what we had scheduled, but actually I think this is okay because it is a very important point that I feel sometimes is not so shown in the training and workshops, but I feel this is really important for, especially for the young researchers, to understand that EBRAINS is just not just floating in space, isolated from society and developing what we feel is the coolest technology and we have always wanted to do. No, 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 it doesn't work like that. We really are integrated and surrounded by a co-design framework that allows us to exchange constantly with our stakeholders. But on top of all of this, there is a lot of discussion about the ethical development of the infrastructure and the impact that such an infrastructure can have in society. There is a dedicated group of people within EBRAINS looking at all these questions and keeping an eye that whatever we do has a focus on promoting human rights, on making sure that whatever we produce is can be trusted, that can be that promotes a positive impact, to make sure that we prevent problems that might emerge from dual use, or also from not considering some minorities in our hypothesis or development. They also make sure that we have a space where we can reflect about ethics, which is really an important thing. And we inside of EBRAINS are definitely committed to addressing these questions, because understanding the brain is just the first step. But what we want to also make sure is not only to understand, but also make sure that there is a benefit derived from understanding it, and to help the stakeholders get the best out of this infrastructure and this investment. So this means that it also has to integrate societal values into the design. We constantly, as I mentioned, exchange in these with the stakeholders to make sure that we also follow this equality, diversity, and inclusion and guiding principles in research. And we try to always collaborate with other initiatives to improve the scientific research, but also involve as much of as a diverse stakeholder base as we can. And because I know this is a topic that is very frequently, or for my previous experience, this is something that young researchers are usually very interested on. I want to ask you to, maybe if somebody wants to share something. Do you have any, or you want to share something that you feel is a very critical ethical question that we should always keep in mind when we work with eBrains and when we do brain research or when we want to design future technologies for brain health? What are these ethical questions that we must always keep in our minds? Does anybody want to contribute? Just raise your hand, and there are no wrong answers. It's just to get to your view, because I've experienced in other young researcher conferences and other workshops that this is a very driving topic. So I want to give you the floor now if you want to express something, experience something.
Can I?
Yes, sure.
Was what I was wondering about. It's like if was someone discovers some differences from some neurobiological differences in, for example, um, different genders or different races, like how to behave in this sense, since it's like a historical problem in this sense in the sociocultural and biological domain.
Yes, that is definitely a very important point, Simone. I think this has been abused in the past, unfortunately, when it was not so easy to keep an eye and validate what the outputs of a research had to do, and also abused in a wrong way. So, yeah, this is definitely a question that we have to keep in mind, the responsibility of the correct communication of our results, but also making sure that whatever we find out and what it means um, is aligned, or then is properly aligned with our societal values, right? And this is a very important framework. Thank you very much for sharing this, Simone. Anybody else who want to raise a point on ethical questions? Okay, if we don't have any other points, you can, of course, well, you will have an opportunity to leave your thoughts as well in a space that we will start in a moment. Um, but if you have any concerns or questions about this, you can also use the support system to write them down and ask, what is eBrains doing to ensure that this doesn't become a problem in the future? So a question also the infrastructure in this sense, please, because it is important to know what worries you. We might have missed something, and we want to hear from you what you expect from the infrastructure as such. Okay, so to end this blog, I want to share a quote from Nicola Palomero Gallagher. She's a professor in Düsseldorf, and she's also the scientific lead of the German National Node. And this is part of the brochure for the eBrains research infrastructure. And she mentioned here that eBrains has really allowed her to accelerate her research. And I think this is not only because our methods are fast and are tested or the simulation tools are great, but also because having this already provided, tested set of tools that just work together for some workflows and for some use cases, this can really become an advantage for you when you're trying to do your work. So it can really provide you like a trampoline to start already quite ahead in answering your questions. And with this, I would like to close the first section and let us take 5 minutes and 3 minutes. Let's at 09:45 we start then with the section on how to do your research on EBRAINS. Okay, just for a quick stretch, maybe get a glass of water, and we're back in a few minutes.
Sandra, if I may ask, I am available today. Is there a specific time that you want me to be?
Okay, we had a very, very short break to stretch and take some water. Hope everybody is back. And yeah, now we have a little bit of an interactive part that has to do with how to do your research in eBrains. We're going to come back to this at the very end of the day when we are going to have questions and answers and look into other things. But one of the critical things that I want to tell you about how to do your research here in this environment, in this very complex infrastructure that has so many tools and that at the moment might look a little bit difficult to understand as a whole, what are the capabilities that you may reach, is that you first have to consider that eBrains is an infrastructure that can support you throughout many different stages of your research, from the conceptual side, to the data gathering side, to the exploration of hypotheses, the analysis of data that you have collected or that you have available, the collaborative effort, the writing of your manuscripts, the publication and sharing of your results, even creating a community around a tool that you developed or an insight that you find out and you want to move forward together with other colleagues. So EBRAINS really is an overarching environment where you can really find a lot of things to support your research. Very quickly, I'm gonna give you a set of suggestions on how to start approaching this. And in a minute, we're also gonna hear a bit more from the science support team, who are more dedicated to understanding your workflows, your use cases. So when you get started in the EBRAINS research infrastructure, it's important that you create a concept for your science. So at what level are you working at now? And first of all, what's your use case? How does it look like? And what are the main features of your use case? At the moment, I am just looking for a tool to create a model. At the moment, I need something to understand the data that I collected in my lab. What are the main features of your use case? What is my overarching objective, right? So what are the steps that are involved in my scientific process from the beginning to the end? If I want to connect the data that my lab is producing experimentally, or I have some clinical data that I have been granted access to, what do I have to do to, I don't know, create a model of how these dynamics emerge from the brain, how to analyze two different data sets? You need to identify all of these different steps because there is the right tool for each job. And thanks to EBRAINS, you can find them all together in the same place. Another important thing is what type of data is involved in my use case. Is it just experimental data gathered, I don't know, from looking at a cell culture? Or is it personal data that was acquired from recording the electrical activity of a living person? These two types of data are completely different and they need to be treated in different ways completely. There, yet again, we come to the ethical side. Some of this personal data has to be treated in a particular manner, not only because we want to respect the person to who it belongs to, but also we want to make this in the frameworks that are legally applicable within Europe. And these two things must go together and integrated in how you do your research. And EBRAINS can help you identify how to address these questions. And another point is, how do you expect others to use the same workflow? I think we are past the time where scientists used to do something in their lab and it would be something that they could only do in their lab, and it was only done once, and it was taken as something that was then a truth. This is definitely not the case anymore. You need to ensure that other scientists can reproduce your results, understand the environment in which you produced your results, and also understand how you analyzed the data that you produced in order to arrive to the conclusions that you are sharing. So in this sense, you also have to think, when I'm finished doing all of these things, how am I going to share this with the world, right? So I will probably write a paper or create a tool and open it in, I don't know, an open repository. But then how do I grant access to the users or other researchers who want to do this? And what if, how can I define the specific set of tools that I use to analyze my data? Maybe my data is gigantic and you cannot analyze this data on your laptop, so you need computing infrastructure dedicated to that. How do I combine these two things? And definitely EBRAINS can help you with each of these steps. But it's important that you start thinking about all of these points when you start engaging with the infrastructure. And because we're going to do some exchanges during the day, and because I want to understand better what is your general background, I mean, for the EduBrains participants, I mostly know already your background, but I also want to know what questions you have and what are your expectations about eBrains. And I also want to provide you a space where you can leave notes that you can leave to us and that we can take into account for future presentations, future modules, and so on. So I have left a link in the chat. This link will take you to a mural. This is not an eBrains tool, but I find this very useful to exchange with others. It is a white space. I think there is only a sticker that I left there. So you please feel free to copy that sticker or create your own sticker. What I really want is that you take some time there trying to reflect a bit about those questions here and translate them into what is your background and how do you want to make use of EBRAINS. We will have time for this in a minute. But first, before we give you some time to basically put out your thoughts in this space, I would like to also ask my colleague, Wouter Klein, who's here today from the science support team, and to continue moving forward those questions and maybe help formalizing them a little bit more and at least discussing with you what is possible from the support side. So, Wouter.
Good. Thank you. Thank you for introducing me, Sandra. I am Wouter Klein. I'm one of the small parts in EBRAINS that is trying to make things clearer for people in the support, both the first line of support and also what we are calling science support. I think I want to share my screen. It should be there. Perfect. Yes, I'm not alone. Marissa is in the meeting, is also part of the science support team. Katja, who is on her way to Japan at the moment to also talk about eBrain, so she could not join, but also people from RISE in Sweden and people in Sinica in Italy. So we have a broad group all over Europe in place to help you or help people navigate the complexity of eBrains. Let me go to the next slide. And what we're aware of is that this can't be done by us alone. This is always done in what we call a co-design fashion, where we really try to bring you as a researcher and other researchers along in this journey to navigate what we do in eBrains in co-design. So we go to the technicians, we go to, like Sandra said, the ethicists, we go to the communication department. Maybe you want to have a nice way to sell your story. So this is where we come in. We help as a science support team you to navigate this complexity. We have tools for this, complex tools, simpler tools. It depends on what you want to do. And we do this in an interactive way. It is not a one-size-fits-all solution for what you want to do. So one important thing that we do is to formalize technical and scientific workflows. We have been doing this for a while now, so we have quite some experience in asking the correct questions from scientists to move their wild ideas into something that's actually actionable. Smaller parts, smaller components that we can actually match, for instance, to tools that we have in eBrains. And what we also do is, because we are getting all this user feedback on the first line support, we know really good what is not working. So we actually start new initiatives to address challenges that we encounter from you as the user. We are the central contact point for support. Sandra introduced this three-level back support structure in eBrains. In the middle here is the science support team. We do the front line. We do some of the third level support. So we have a complete overview of all the lines of communication and support that we have in eBrains. And further, we also try to initiate collaborations. This can be very small. Somebody comes in and say, hey, I am interested in brain simulation. We can send them to the brain simulation experts. On the other side, we might come across people from, like I said, Japan. They are interested in collaboration. So we try to then initiate collaboration, even at that level. So the science support team in eBrains is a flexible team of experts. We know a little bit of all different things and try to help people as much as possible. The co-design, what we do. On the top, we assess the project needs and requirements. So do you need data storage? What type of HPC resources do you need? What tools do you need? We can engage with the different experts in the project. We can help you talk about ethics, an education program. How do you want to maybe teach your tool to the environment, to the public, and the communications? We facilitate reproducible science by very clearly documenting the workflows. not in code, but in words, so that people can interact with it and that you can make your documentation out of this. Then we try to arrange consultation and coordinate between cross-disciplinary sections. Typically, we try to get people together in a room, and we then set the agenda, we ask the questions, but then let you as a researcher talk to the experts. We facilitate and make sure that people come together and have the right topics to talk about, because that is sometimes a challenge, that you as a scientist do not know what you might need from the experts. And this is where we come in. We've done this before, and we will ask for you the right questions, and sometimes the other way around. We'll ask from you the right questions so that you can tell your challenge to the experts. And this is a constantly developing project. This co-design process that we talk about, we even try to improve this process constantly. And your needs also change during the maturation of your project. What you need from us at the start of your career is different than what you need at the end of your career. What you need at the start of your research is different towards the end of the research. So this is really an iterative, self-improving process where we try to be in close contact with you to help your research further along. And I think that was it. Maybe here at the end, some last details. Our email is sst@ebrains.eu, but if you send an email to support@ebrains.eu, it's the same people. So you can use these two options. If you put EduBrains in the subject line, we know that it's coming from you. So that is a way to steer it a little bit in the correct direction. And the support team is me, Marissa, Katja, and Anastasia. And with that, I give it back to Sandra. And really, if you have questions, don't hesitate. Do understand that we are not an expert in anything. So it could be that we send your question to an expert and that it takes a little bit longer. But I think this is what to be expected from something as big as EBRAINS, that there's nobody that knows everything. Good, I think, that was me.
Excellent. Thank you so much, Wouter, for this, and Marissa as well, and of course, Katja and Anastasia, who are also helping with this great effort and also to put together this information for the participants. Of course, everybody, please feel reassured that we will also make these slides available for you, so you will have all the contact information required. But I think as Wouter mentioned already, and I also mentioned in the beginning, we are happy to hear from you, so contact us. And we will definitely try to route your questions throughout the eBrains system so that you can get the best out of them. Okay, so I would like to very quickly share my screen. Just a second. My computer is taking a little bit of time. I see that some of you are already in the mural, which makes me very happy to see that you are already engaging in this space. Okay. Yes, I found the right screen. Okay, so I see that you are already creating your stickers and adding your information. Please feel free to leave here your comments. Take a little bit of time to write about what you expect, what you want. You probably can make this a bit larger in case.
Could you send the link in the chat again?
Yes, sure. happening. And okay, thank you, Valentina. Perfect. Yes, so with the questions that you had in mind, please that we discussed in mind, please write down a little bit here. Throughout the day, I invite you to come back to this mural and leave notes for you. For example, when you identify an interesting tool, yeah, write it down, make a link, add a question, leave a thought, okay? So later we can also understand what are your requests, what are your ideas behind the program, and that we also can make connections later with throughout the different modules in the EduBrains program. Very good. Before I actually give you some space to do this and give you some time before our break, I want to share something else with you. And that is the first phase of our treasure hunt. Okay. So here are the first 5 questions for the treasure hunt. I will give you the rest of the time that we have. I think it's about, 20 minutes to write in your mural what you think, what are your expectations, what's your background, what you want to do with EBRAINS, but also to go around and try to find the answers to these questions. The words that should go in this bracket type of symbol are the answers, and you need to basically collect all those words and use the first letter of all those words in the end to come up with the final message of your treasure hunt. I hope this also helps you navigate a little bit the first thoughts that we shared today about an introduction to EBRAINS. And I will leave this up for the next minutes. And after you have spent some time there, we have a short coffee break in our program. So we are basically restarting at 11 from now with the data tools in EBRAINS. I thank you very much for your attention on this first part of the module. And if you have questions, I am here. So we can exchange if you have anything to share or to ask in the chat, or also if you have something to share in the mural. Okay. Thank you so much. And then I leave you a bit. If you have also questions regarding what you should, something that you want to add to the mural or something that you would like me to look into, just let me know. I will try to interact a little bit with you in the mural in the next minute. So, perfect. Valentina, did we stop the recording already? Or is it ongoing?
I will stop.
Okay. Okay, everybody, welcome back then to our module. And let us get started with one of the core elements of the EBRAINS research infrastructure and this vast ecosystem of tools and services. And these are the data services. EBRAINS has become very strong in providing elements that allow you to share, find, and explore data of different types for many different purposes. And so right now we're gonna dive into these services first, just as an overview, and then we're gonna use the EBRAINS website to navigate into some of these tools and to give you a glimpse of what they are about and how you can interact with them. Again, as I mentioned at the beginning, your eBrains account is very important to work with these data services. So that is definitely something that you need to have before getting it started here. And so the first very important element of the eBrains infrastructure is the knowledge graph. The knowledge graph is basically a collection of metadata that links to data objects. These data objects can be basically anything digitalized. So this means data sets of different types, models, workflow descriptors, software tools, and we have here a few examples. We have a data set on the left for this ultra high resolution 3D cytoarchitectonic maps of the of a specific area of the brain. On the right, we have a model that is very popular and was developed to understand better the macrovisual cortex. This is a mathematical model for NEST. That is a simulation tool that we will look later into in more detail. And in the lower part, we have a software tool, which is Unicore. Unicore is a tool that allows you to submit jobs to high-performance computing infrastructure, so workloads of compute. If you have something defined in your laptop or on the eBrains collaboratory environments, you can use Unicore to deploy things on HPC, but even also to interact with neuromorphic hardware. And it is a very nice element of connection that kind of works in the middle between the different infrastructure services. So these are just examples of things that you can do. But then how do I get to work with the knowledge graph? Well, first, let's look into the process to put data into the knowledge graph. So to put data into the knowledge graph, you have to get it curated. Why? Because EBRAINS makes sure that everything that is integrated into the knowledge graph has been controlled and checked for that is complete, that it's accurate, that there is a specific level of quality, but also that it's documented. So that we have enough information in form of metadata so that people who want to find it or reuse it can make the best out of it, right? So if you want to curate your data, let's say your lab produces large amounts of electrophysiological data, then you get your data, you fill the request, which you can find in the shared data section of the services for data curation. And then you can submit a request. You can also directly contact the assistants in curation support. And you can also use the support channels that we mentioned before to start or trigger this curation process. In the end, what is important is that you know what your data is, that you describe what your data is about, where does it come from, what can people do with it, what should people say when they are using your data. Maybe one of the biggest issues that has hindered some communities to share data is that there is the fear of not being recognized for the work that took to produce the data, or even to lose track of what the data or how the data is being used for. So it's important that the EBRAINS knowledge graph provides a DOI and an element that is fixed and long-term that can be used to make reference to that data set and or this code or this model. This allows researchers to feel more confident about sharing and for other scientists to easily reproduce the results of research if there is a permanent link to the data that was used to produce the result that was shared. Yeah, so one other beautiful thing about the knowledge graph is that here you saw the graphic user interface that is web accessible, but you also have a programmable or programmatically you can still access these data sets. So you can search for the knowledge within the knowledge graph programmatically. You can query data sets, you can download them, you can use them by utilizing a Python interface, which is very, very nice, because then you can integrate it into a whole workflow, into a Jupyter notebook, into your research steps very easily. So that's what you need to do. And you need to know about the data curation in a knowledge graph in very, very simple terms. As I mentioned, these services are provided by different colleagues in different parts of Europe. There is an amazing team behind the knowledge graph, taking a look at all these curation queries, and it is really a lot of work, because it needs it requires that you take a lot of consideration into all the details for the metadata to make this usable, and in the end to enhance the quality of such a resource, a very important resource. So yes, if you have more questions, you can of course go to the data curation section, either in the collaboratory, that is this wiki link, or within ebrains.eu. You can, in the knowledge graph section, also look for more information. Okay, so that was the knowledge graph, and we will navigate in it a little bit more later. But let's move to the next service. And the next service is the atlases. At the moment, we have many different atlases. This, for example, is the multi-scale, multimodal human brain atlas. But we also have now a macaque atlas, a rat atlas. We have a variety of data sources being integrated into this viewer. And what is very interesting is that you can use this, of course, to explore brain structure, to understand better the cytoarchitecture of the brain at really different levels of detail, going really to an extreme level of detail. But it also combines other information, for example, molecular, cellular, and fiber architecture, which is very important if you want to create a good basis for the structure of the brain and to understand how this even impacts function in different ways. So you can also see here, we are seeing here the integration of connectivity into these atlases. Within the current project, EBRAINS 2.0, there is a big effort to integrate the different modalities of data, which will be then linked to the atlas in some way to allow the users to explore this data in the same reference space. Again, here, one critical and very important feature is that there is an API to query this data. So you don't need to get the data only from this graphic user interface, which is really interesting and beautiful. It looks really like a spatial navigation environment. But if you want to programmatically extract features from the brain structure to integrate them in analysis or modeling or to create further hypotheses, you can do that programmatically via this API. Okay, moving forward, we have another service that is quite different in nature. So the EBRAINS live papers basically allow you to share your manuscripts in an innovative way, let's say, with the community. Here you can create versions of your papers, of your produced papers, where you can integrate other means of analysis and visualization of the data that was produced. And we will see some examples at the end when we start navigating the site. But this is a quite different way of communicating research and also of storing data that should sometimes this is added as in a manuscript. When you submit your manuscript to a journal, right, you add additional data or supporting data to your manuscript. But this is a way in which, so the live papers provide you a way in which this becomes a lot more interactive, and there is the potential to express a lot more of the insights driven from the information that was collected. Okay, so regarding data and data exploration, data sharing, these are some of the main core services. But important to EduBrains are also the medical infrastructures that have to do with personal data management, access and user interaction. And some of these services are open to a certain extent to the public. Some others require a specific level of authorization. So you will not be able to immediately access some of these services. You might need to request access explicitly, and in sometimes you will have to explain why you want to access specific sets of data. But the medical analytics and processing infrastructure from EBRAINS gives you next level access to very important data that needs a special protection. And this is why there is an enhanced level of restriction about it. At the moment, we have 4 platforms in EBRAINS that have to do with medical data. The first of them is a medical informatics platform, and here I may take the chance to thank the science support team, and actually I think it was Marisa who generated some of these nice pictures based on the information that we have been collecting from the different services, but also based on what the colleagues from the medical informatics platform shared. And this is all parts also of the tools book that I also added a link in the chat to. Yes, so the medical informatics platform is a place where you can analyze data in more anonymized way. It collects information from different hospital databases and allows you to see higher level metrics derived from this collection of data. But it is important that the data is not moved from the hospitals. The data is processed in a distributed manner, and what the user sees is basically the result of a statistical analysis or predictive models or machine learning tools that are acting on the data. This approach then keeps the data protected and secure, so the patients are not worried about their data being leaked or shared with people who are not entitled to access that data. But on the other hand, we can get a better understanding of the general features of data coming from these hospital databases and sources. So this approach is a way to circumvent some of the problems that are related to dealing with personal data in an efficient way, and also keeping the data anonymized for research purposes. Of course, this is not always possible. Sometimes your research question needs more insight into the personal data. And so we have other platforms where this is dealt with in a different way. So we have, for example, the Human Intracerebral EEG platform, the HIP, which is also a collaborative effort that combines information being produced at the international level by different European partners, and that ensures data privacy. But although the HIP was originally only intended to work with EEG, now they are also expanding to other data forms or data modalities. And there are some ways to have some more computing intensive work being done, or workloads being done inside the HIP, although not very very intensive, but at least it has a support to do some workloads that might need a lot of memory or compute resources. And yeah, the users of the HIP have to come from authorized institutions. So if you apply, then you have to go through the process. Well, first, if your institution is already authorized, this might be faster. But if it's not, then you have to go through the process of getting your institution authorized to access the data. And this is because the access or the security to the data sets needs to be preserved. This is a very collaborative initiative, and more data elements are integrated into this platform. One interesting thing is that many of these platforms use the data standard BITS, which allows then interoperability, and BITS is also a very frequently used standard in the community. So by aligning with this standard, we also hope to enhance reproducibility in the whole EBRAINS platform. As I mentioned, there's a big push for standardization, and this also allows us to connect across different platforms. We also have the EBRAINS Health Data Cloud. The Health Data Cloud is really an environment where neuroscientists can have data put into, for example, a green room, and then pseudonymize the data or process the data and work with it within a very well-defined legal framework. One of the best features of the Health Data Cloud is that it works as a distributed set of nodes that share the metadata only, the non-sensitive or non-personal data through metadata, so that researchers, through the knowledge graph as well, can find these data sets that are maybe located in different areas in Europe, and then they can request access to the local node to do some processing of that data. That way the data doesn't have to be moved, but still we allow the research consortia to make sure that the data they produce is being used correctly, and on the other hand, the data that they want to use from other groups is accessible in the best way possible. Using the Health Data Cloud, of course, also requires that you establish agreements between the data protection officers from the originating, so the institute where the data is being originated, and the the node where the data is being processed and the person who is accessing the data to do research. So there are many actors in this legal construct, but these platforms really aim at providing solutions to make the best out of the data that exists for clinical purposes, being always compliant with the European regulations. And inside of the HDC, you find also many tools that we will see in the next hours, also from the infrastructure that that are useful for modeling, for analysis, for simulation, for visualization, and that way all of these services get integrated horizontally. Finally, the new kid on the block is actually the platform from human imaging. This service is being developed at the moment within EBRAINS 2.0, and it is meant to collect one of the most ambitious data sets that have been really recorded lately, and or it's being collected currently. It's called the pentamodel data set, which includes 5 different modalities of recording for the same that are being done on the same set of subjects. And so this nice data set to different degrees will become accessible to EBRAINS users for analysis and further work with. This is still in work in progress, and at the end of this year, there should be more information on how to get access. As mentioned, at least for the 5, so the platform for human imaging, the HIP, and the HDC, in some of these nodes, you need to request access directly. For the medical informatics platform, you need also access. You can request it to see more, but there is a public-facing service that also provides very generic example data that you can see for yourself and get an idea of what are the possibilities that you can get in this platform. Okay. So this is the summary. And I see there are a few questions, but I will read the questions. He asks, is it possible to reshare data sets and resources that have already been shared in other data platforms under Creative Commons license? This is a very good question. I think you can. It is important that you fill all the information, all the requested information still on the metadata curation request. I would, if you want to do this, this is probably just connecting to another knowledge graph or another data source. I would send a support ticket to the curation team to ask them about this specific data set. Then they can tell you exactly what data they need and how to best achieve this. Because I wouldn't be able to tell you myself which would be the legal restrictions or if there is anything to consider. But yes, I think asking directly the curation team is the best thing to do here. And Omar also asked, does the knowledge graph database can be easily connected to an LLM for guided domain-specific research purposes? Yes. So basically there is a tool that already allows you to query data sets from the knowledge graph programmatically. So basically you would have to create a script that queries all the data that you want to have So first finds out which data matches your filters, what data you want to have, and then make all the requests to gather the data, collect the data, download it, and then use it for the training of your model if you want. There is we don't have at the moment yet such a layer already available in EBRAINS, but because the programmatic access and the API is already there, creating such a script shouldn't be too problematic at all. Okay, then other questions? If not, then let me quickly. So if you go to ebrains.eu, right, you have this entry section that I briefly showed in the introduction, and here you can navigate the site and take a look at all the different features of eBrains and get to know a little bit about the research and the events and so on. And on the top part, you will see this navigation site. And let's start with the live papers because we were already directing there. So you can either publish your live paper or you can also browse and search live papers. And here, for example, there are some very nice publications that are also connected to, so these live papers do not replace a normal publication, of course. This paper, for example, was submitted to PLOS Computational Biology. And here is the abstract, but then what you can do is that you can add some other things. You can add, for example, Jupyter notebooks that allow you to validate the models and to see, for example, how things match the literature. And if you click on view, this is automatically connected to another part of the infrastructure that is the lab, the Jupyter lab. And here you can, of course, sign in with your eBrains account and then give it permission to start everything. Take a little bit of a little moment to charge everything, but then you have access to these Jupyter notebooks and you can start exploring the data and everything that was provided as a side element to that paper. So you can start executing the different sides of the different sections of the manuscript and analysis and follow also what the researchers were thinking when they did all this process. So if you see here, it is a far more interactive way to exchange with the community also all the code that was produced to generate the outputs and to create visualizations, for example, right? So this is then a lateral connection between the live papers infrastructure and our Jupyter lab infrastructure as well. We can leave here, and of course you can also look at the models that were used, look for other connections to literature, and so this becomes a really interesting way to provide additional information to your manuscripts. You can also, of course, publish your live paper, and then you are directed to, of course, I have to authenticate myself with my account, but then, for example, you are directed to this builder where you can create a new uh, um, a new live paper, you can upload the PDF of your existing manuscript, or you can specify a DOI so the main data is already extracted from your main publication, and then you can move forward and yeah, add some elements here and create a preview and then save and submit your live paper. So it's nice and straightforward. It's an added asset for you, especially for young researchers that you are doing your manuscripts, maybe contributing to your thesis or doing during your postdoc, and you want to add an additional feature to your research that will also be searchable and findable in the future. Let me now quickly, I think I will just share my whole screen. Then you have a little bit here, this bar. I will hide it so you don't see it. Okay, so here we are in the knowledge graph instead. So I went to ebrains.eu and looked into the knowledge graph that is quite straightforward in the data services. So you go here and you go to find data, and then you are directed to browse the EBRAINS data models and software, or you can also explore the data sets using the knowledge graph. So you can just click here, and this will take you immediately to this site where I'm looking here. And you will see that there are a large amount of data sets themselves. You have also different models. For example, here a nice recently added neural mass model for neuromodulation. We have software tools like the virtual brain inference or the FAIR graph. And when you go into them, what you get is first an overview of all the contributors in terms of the software, but also the data sets are, you can see the version of this, so they get updated depending on the releases that are done, and so you always have a track of the actual version that you're using. You can copy here to the clipboard that search link so that you can use it to share with others. You have here more information about the actual DOI that is provided to this software item, when it was released, and some details about what it is. In this case, because it's a software, there's also specifications about the version and so on. It tells you with which platforms you can use this, and of course also the programming language. If you instead select a data set, for example, this Yulish brain atlas maps, you can of course also see again the list of contributors to this data set. You can get the DOI, and you can have more information about which techniques were used to generate the data, what is the experimental approach, and you have usually also links to more information about the data. It tells you here how to cite the data, so how you could use it in your manuscripts, and so how to get the data. So you can here download the data set directly, or you can use the specified DOI and links to download them programmatically. It has the publications where this data was originally published, as well as a list of all the different, in this case, specimens that were added. This can be subjects, this can be recording items, sessions, depending on the type of data that you're looking into, right? And some hints about how to use it. So here is, for example, the way to query this programmatically using the knowledge graph query builder, which allows you to then create an actual query for this specific item, and you can add more information about how to use the REST API to pull the data and use it in your code when you want to work forward. So as you see, you have here in the knowledge graph all the information that you need to work with these data items. And of course, you can here explore and search for different, using different filters to get all the data that you need. If you want instead to share the data, as I mentioned, here is all the information that you need in order to request the curation of your data sets. And of course, you can also contact the support team to get some help in getting your data into the knowledge graph service and make it fair. Yeah, so this is the knowledge graph. And now we move to the other data item. This is the atlas. We mentioned that already that there are many different atlas available. You can find the atlas by going here to data, tools and services, and then selecting brain atlases. And here is more information about this. What I did now was to launch the 3D Atlas viewer. And what that does is that it brings you here to this Zebra Explorer, where now, so in the previous versions, it was only possible to see the human atlas, but today you can choose for many different atlases, as you see. So it's the monkey atlas, the rat atlas, the mouse atlas, and the marmoset atlas. And you can choose between different parcellations as well. You can also look for specific regions of the brain, for example, where you can choose specific areas and get more information about what we know about this region, what is the data that was already collected here. For example, there is information, macrostructural information about the area. There is also the possibility to extract the connectivity, the functional connectivity to the region, and to understand how different regions in the brain are connected to this specific region. So you really can extract a lot of structural information by navigating this, of course, let's say in this graphic interface, but you can also do this programmatically, which is really powerful because then you can integrate all this insight and information that you collect quickly into any modeling approach that you may have. You can also create download the current atlas view. So if you want to use it for a publication, for example, and if you log in, then of course you have a few more features that are also being registered in your personal user space that we discussed at the very beginning. When you log in into the EBRAINS site, then you will get some recording of the information that you have been or that you visited this service at some point, and it becomes like a favorite feature that is then shown in your own space. So this is the very nice set of atlases that are now being more enriched with more data from all different types and scales. So I'm going to then jump very quickly to tell you where to find the medical analytics platform. So also in data tools and services, you find these medical analytics platforms. We already briefly discussed all four of them. As mentioned, the HIP, the HDC, and the PHI are platforms where you need more authorization to get in. For the medical informatics platform, this is also the case, but you can also enter the public section if you want to get an idea of how this works. And then you can start looking at these anonymized analysis outputs that are available, so you get a feeling of how this informatics platform works, and maybe you can already start thinking about questions that maybe if in the future you would like to have access to more specific data sets, then you can request this access specifically based on your research question. And here you see the amount of data, the type of data that is becoming available on these different federated parts of the medical informatics platform. Yeah, as mentioned, the FI is still under construction, but hopefully very soon it will be, well, it's still possible that you ask for access, but the data is still being collected, so there's still a lot of work to be done in the platform. And for the HDC, you can also try it out in more generic way. Of course, you need to log in with EBRAINS. Your EBRAINS account is key again. And then this is a version of the HDC where you can explore a little bit the infrastructure, but at the moment, this open version does not allow you to process personal data yet. You need to or create a specific project with some specific features in the right nodes in order to get access or to be able to upload or utilize personal data. At the moment, this is basically an open general playground where we can understand the platform, see how it works, and then get a better overview if this is exactly what we would need for our research, and then try to work forward with them. So you can also access this, let's say, more free explorative instance of the HDC. Yeah, so as I mentioned, for EduBrains, this is really important. So I hope that you got a good overview of all these platforms and what is possible at the moment, what needs a little bit of more authorization to get into and to work with. Okay, so questions. I see that Omar also had another question. He said, I was wondering if there is a GitHub resource with examples or notebooks showing how to make use of the knowledge graph. Yes, there is a lot of information in the form of examples and notebooks, and we will get to that a little bit towards the end of today. So there is a great space full of tutorials, workshops, videos, Jupyter notebooks, examples that have been collected by the Education Task Force of EBRAINS. But additionally to that, you can find a lot of information also in the collaboratory, which is another space where you can share information. Important to say is that the collaboratory, some of the collabs might be out of date because they are produced by users as well as developers throughout time. And of course, software versions change. So you always have to be careful when you go into the collab, you check an example, make sure that it is up to date to the latest version of the software. But if you have questions about the collab as well, you can always send a request to support. And there are many nice examples about how to grab data from the knowledge graph, how to grab data from the atlas, and we will look at them with care in the almost the last session, so in the collaboration part of today. Any other questions? Do you find exciting to have access to this type of platforms? Do you find it interesting and also useful for the type of questions that you have? Yes? Okay. Very good. So within EduBrains, what we really want is that you become power users of this infrastructure. So I hope that for the ones who have also questions that may make use of some of this, you also try to approach getting access to these resources more thoroughly, and you give us your feedback on how this is helping you trying to formulate your questions in the best way possible, being respectful of the data protection, but making the best out of the knowledge that we have collectively put together. Okay, very good. Yes, again, I am definitely not an expert in any of these single tools. I am mostly a user of these tools as well, because my expertise is more on HPC and simulation, but I've used many of these tools, and for me, it is also a nice thing to have this cross interaction between the infrastructure, something that is quite unique to eBrains, and where you can really leverage the best out of the different services. And the colleagues that contribute to the data services really put a lot of work to have not only graphic interfaces and user-friendly facing interfaces, but also to provide the right tools in the back. So computing with all of these resources and automated querying and grabbing of data is very, very made very easy, or as easy as possible. Okay, then it's time for the second set of questions from our hunt. And if I manage to share this correctly, just a moment. I will start from the current section and then put the questions in the chat. If you can't answer some of the questions yet because we haven't seen all of these things, don't worry, because you will get also information about these tools. But maybe you can already start trying to find out what are the answers to some of them. So we are at the end of this section of today. We have now our lunch break. We see each other back at 1 for very intensive introduction into the modeling and simulation tools. We have a really large variety of tools that is going to be quite extensive, but I hope it's also interesting for you. We will go through that and then dive into the high performance computing, neuromorphic, and AI methods as well. So I thank you all for your time and attention until now. I wish you a very nice lunch break and that you come with a lots of energy. Please don't eat too much sugar or carbohydrates so you don't fall asleep during the simulation and modeling session. Sugar rush or sugar down break. So let's hope it is a very nice session then at one where we really look into all of these possible features for brain simulation and research, visualization, analysis, and so on. So thank you all. If any question comes while you are having lunch or before that, always feel free to leave questions in the chat and we will address them as soon as we're back. So thank you all and see you in about an hour. So let's get started because we have many tools to visit in this section and yeah, it's going to be a little bit longer. I think. So let's get quickly started, and I think maybe other colleagues will start joining in the meantime. Yes, so this section has to do with simulation, modeling, visualization, analysis tools within the EBRAINS research infrastructure. Again, as I mentioned at the very beginning and the other section, I am not the developer of all these tools. This is a collection of information from colleagues who have contributed, developed, put out all of these tools. So here I am working just like a guiding tour throughout the whole ecosystem. I may know more about some tools than others, so I can answer some of your questions or at least direct you to the right people. But in general, the goal of these sessions is that you get an overview of the tools that exist. And also, as I said, there are so many tools in the EBRAINS ecosystem. It is not possible to look at them, at all of them during this session. So this is just a subset of some of them that I thought would be useful for you within the EduBrains program. But please visit the toolbook. I added the link in the chat. And there is also the EBRAINS handbook where you can find more details about the technical features of some of these tools and services. So keep them at hand as well. I also added again the link to the mural in case you want to take notes about the tools that you feel are interesting for the use cases that you're developing in your mind and how your approach on how to use the EBRAINS to the best. Okay, so EBRAINS has to do with understanding the brain, and to provide a set of tools to do that is very complex because the brain operates at many different scales. There are many phenomena going on that is intertwined between spatial and temporal scales. EBRAINS provides a wide variety of tools to address questions at each of these scales, but also ways to work together and extract features from one scale to the next and use them to understand better emerging phenomena. Most of the tools that you will see here can also produce outputs that can be connected to analysis and visualization tools. They can also be compared to outputs of a neuromorphic hardware. Some of the models are compatible to be executed both in simulation tools as well as neuromorphic hardware. And of course, there is the possibility to use high-performance computing, which we will see in the next section, to accelerate some of the simulations. Usually, the more detail is the scale that you have to deal with, the more computationally intensive the simulations are. And so it becomes more reasonable to make use of high-performance computing infrastructure. let's get started with the subcellular scale. And here we have a nice ecosystem of tools that are partially developed outside of the Human Brain Project, or were developed and have been developed for many years outside of the Human Brain Project. For example, GROMACS is a very well-known tool in the field of simulations for molecular dynamics and biomolecular simulations. And however, within EBRAINS, it has been made possible to integrate some of these features, maybe towards Jupyter notebooks, or to create analysis and outputs that can be used for this multi-scale simulation signaling network models. Some of the things that go around, for example, subcellular workflows are, for example, the integration of gene expression in some areas of the brain that can then be used to create workflows to predict molecular structures or neural biomolecules, and then use those to exploit this molecular information in a biochemical network to create models and multi-scale simulations. And some of these tools have already been successfully connected into these workflows and provided as Jupyter notebooks that you can find in the collaboratory of EBRAINS. There's also some databases that provide information for these different scales, and you can find also information about how to access and modify these workflows to tune them to your specific question. These are some of the examples. Some of these tools were produced in earlier versions of the Human Brain Project. For example, here you have some outputs of the platforms that were developed in the SGA2, which was the second, let's say, iteration of the Human Brain Project, or section of the Human Brain Project. And there has been different outputs produced from this, including publications, but also Jupyter Notebooks examples and things that work in that direction. So there is, of course, another very important aspect in this subcellular scale that has to do with fitting your model to experimental observations. And this type of workflows that can be used in different modeling approaches aim at converting or switching between simulation tools or frameworks a little bit more easy and combining these tools together. So for example, here we see a workflow where you are extracting some of the main features of a model and creating a model reduction paradigm in order to obtain more simplified versions of the single cell that are computationally more efficient and easier to execute in your laptop instead of requiring large amounts of infrastructure. Of course, EBRAINS allows you to execute these larger models as well, but one interesting thing is if you can create more simplified models, then you can, of course, also move forward and make some tests, preliminary tests, a lot more efficiently. And then you can integrate other parts of the information. For example, here, steps and neuron are combined into some simulation environment in order to create expressions of a cell that has details in its internal mechanisms, internal activity, but it also gives you understanding of the subcellular mechanisms that are going on. And we have, for example, another tool called SNUDA, which really connects all these scales. So goes from being able to define these very detailed morphological models of single cells and optimizing those cells in order to match experimental data. And then you can create patterns of connectivity between these cells by identifying elements in so places in space where these the dendrites and the axons touch, and you can also create or prune synapses, which then leads you to the possibility of creating a large model with all these very detailed cells and being able to simulate these networks. An example of this are these mouse striatum models that have been available since several years now from the colleagues on KTH. Then moving a little bit forward, we have also the possibility to simulate and extract from these simulations local field potentials. And this is, of course, very important because it allows us to create better comparisons between what we observe experimentally and what we observe in our simulations. LFPy-Kit is a tool that really allows you to create or map the transmembrane currents in a single cell simulation to extracellular signals, which is what we usually see when we do electrophysiological experiments. And this is a nice Python tool that is actually simulator independent. So if you have any simulator that works with this type of detailed cell models, then you can calculate the extracellular potentials around this cell, feeding the outputs of the simulation of the cell activity in the membrane. LFPy also gives you different mechanisms to analyze the outputs and correlate them to your model. And it works with different tools that we have available in the EBRAINS ecosystem. So it also allows for this horizontal connection. There are a lot of examples available on all of these tools. So you will also see that I have put here some links to GitHub repositories, but also there are a variety of collabs that provide examples, and we have also tutorials that we will see a little bit later. When we want to deal with the cellular scale, so single cells, we also want to be able to create models that, as we mentioned before, match our expectations or also observations derived from the experiments that we do in the lab. So for this, we have the NeuroFeature Extracts service, which is a user-friendly web app where you can find already some example traces, but you can also upload your own trace and then select some of the features that you are interested in analyzing, and then you will get an automatic processing of your data set and get those features extracted for you so you can use them, for example, to fit your simulation data against these features, including, for example, interspike times, other features that define the shape of the spike, and many other features that are also already available there. Then we have the neuron builders, and here we have different elements in this workflow. We have this feature extraction tool, but you can also create you can also select and upload different models from the model catalog. You can optimize these cells to match electrophysiological data or also other recordings from external databases. And then you can also do the simulations. If you have access to the EBRAINS lab, which you usually get when you get your EBRAINS account. You just have to log in, and then you can submit these jobs, and you will get the simulation outputs back without having to struggle with going to the supercomputer and trying to figure out how to do it from scratch. This service takes care of deploying these jobs for you, which is very easy, especially for if you are starting with your research and you just want to get an idea of what is possible. This is a great way to get started. Other tools that are also in this family are the small circuit in silico experiments, where you can have a set of detailed tools that, of course, can also be connected, and you can create digital recordings of the voltage traces of the membrane. And you have also these brain area simulations where you already have these large, very complex models that have taken so much time to put together, already available for you in a nice web-based GUI, and you can interact with them. We will take a quick look later at the very end in a more interactive manner. Yeah, so besides those tools, we have also, all of those tools are mostly based on the neuron simulator, which is basically the golden standard for morphological detail neurons. And here we also have Arbor. Arbor is a newer simulation library that aims at leveraging very scalable hardware. So this means that you can really deploy very large simulations on new hardware, new accelerators, GPUs, and large clusters of supercomputers. And the idea behind Arbor is very similar to neurons. So you also have morphological detail spiking neurons, and you can create these in silico experiments, like providing current or stimulating the cells with currents and recording the membrane potential, for example, in different sections of your cell. But then you can also create networks with 100,000 million neurons and create these simulations very efficiently on high-performance computing infrastructure. This is the set of people who are behind it. This has been an effort that has been going on from the Human Brain Project and continues to move forward. And there are different tools. Of course, all of these tools are community tools, so you can contribute, you can exchange, you can request things, and we are happy, of course, if you also contribute to the development. Before we continue, are there any questions so far? I don't see any hands. Okay, then we continue. So we have reached the network scale. Well, already with Arbor, we were reaching between the detailed cells and the network scale. Also, some of the models or the tools with the neuron can do this. But here with NEST, we are now approaching a different level of abstraction. For NEST, which is a very well-known simulator in the field, neurons are no longer defined with all these details, all the dendritic tree, all the details on the axon. It's really compressed into what is called a point neuron. And these abstractions allow NEST to work in a wide range of systems, from your local laptops all the way to the supercomputers. But it also allows very efficient simulations of large networks with hundreds of millions of neurons. And NEST provides a large variety of models, of single-cell models that you can combine with a wide range of synaptic models, as well as plasticity and other biological learning models. So NEST provides you a very rich environment to produce this type of simulations. There are more than 50 neural models now, many synapse models, and they try to reproduce, of course, the experimental observations. So this is why there exist so many different models. And you can work with NEST with a Python interface, and it's designed to make the best out of the combination between being very accessible to users and being very efficient in the back. There are many examples on how to work with NEST. If you the fact that a NEST can be used in many of the other services from EBRAINS, it's very useful because it allows you to test very quickly your hypothesis, but also beyond that, you can use your installation in your computer, or you can use an installation on the supercomputers to make other types of explorations that are have specific needs, right? For example, there are very nice large models like this, the macaque vision area model, which is a larger model, is built with 32 different areas of the macaque visual cortex. And of course, then the computational load is a lot bigger, but this is easily executable on our supercomputing infrastructure. And it provides a very nice experimental or experimentation framework to study how visual input passes through different stages in the visual cortex. And recently, this has also been connected to the atlas. So you can extract all those structural features that are defined in the macaque atlas and integrate them into the model, and then create even more realistic and well-defined models that represent what we can observe with different modalities of experimental measurement. Users who want to leverage NEST to the fullest can also provide their own models using a domain-specific language, a high-level language called NestML, which allows you to define the dynamics of the membrane and define other parameters that you are interested on integrating into your model, and basically produce code automatically without having to code it yourself. So NestML takes care of understanding your equations, your parameters, your inputs and your outputs, and then generates the code on its own. And this allows you to get faster into integrating your own models into the NEST simulator. NestML has also many different backends and can produce code, for example, for the Spinnaker system, which is something that we will see in a few slides. And this is an example, but basically you have your model, then you have the code generation, and then here you have, for example, the different backends to which you can produce the code. And this, of course, enables us to compare the outputs from the simulations with, for example, the outputs generated from the neuromorphic hardware, which is this Spinnaker chip. So it's a very interesting way to also create validation workflows. If you want to use NEST in a more to explain something in a more educational manner, or if you want to use Nest only to test some hypothesis very quickly, you can also use Nest Desktop, which is this graphic interface that allows you to create your models with a GUI, and which also produces the corresponding Python code that you can extend and use further. But it's a very nice way to get started, and it's also great for education purposes. And then we dive into the whole brain scale, and here we have one of the main simulators going in this direction is the virtual brain. The virtual brain is a platform where then you don't have single neurons in space represented by points. That is too detailed. Now we are talking about complete regions of the brain. And we have now dynamical models that tell us how the dynamics, the collective dynamics of the cells in that region work and can be represented as different variables of interest. And here, of course, you can integrate a lot more information that we usually see in clinical applications. And this is why the virtual brain is very appealing towards, in these applications, towards this type of brain health research. Usually, a model in the virtual brain is created by defining the dynamics of the different regions and then connecting these regions using structural data that comes, for example, from DTI, cartography, recordings from patients or any subject, and then executing simulations that match, for example, recordings from EEG or bold signals that are derived from fMRI data. So it is very convenient because it's at a scale where we can actually match information with subjects who are, of course, subject to neuroimaging technologies that are less invasive, and this makes this approach very much more accessible and useful for human brain research. Some examples of applying the virtual brain go, for example, for the Bayesian virtual epileptic patient, which is a framework that allows you to fit the features of a model against clinical hypotheses and clinical data using Bayesian inference. And here, this is an approach that has been very successfully being used in the recent years to try to support clinical research and clinical practice, especially for patients who are drug resistant and suffer from these epileptic seizures. So it's a great element to connect and create hypotheses about what would happen if the clinician decides to perform a surgery and take away a section of the brain in order to help these seizures go away. And what will be the effects of removing this section, and to understand all of this in silico before actually creating or performing the intervention. Just as with Nest, TBB also has its domain-specific language, which is called RateML, and RateML produces code in Python and CUDA, where you can then create large amounts of different parameter combinations of your model and try to explore which ones are the best fitting to the clinical or experimental data that you have available. And this was one example that I already showed at the very beginning, but towards the end of the Human Brain Project, it became very clear that it was important to formalize this type of workflows where you have the data in the atlases being fed to the models and then put into simulation, exploration, analysis workflows running on supercomputers, then producing scientific validation and moving cyclically to optimize the outputs of these workflows. And this combined horizontal connection, again, is one of the unique features of eBrains. Of course, if you are discussing about working with the brain, and we mentioned that the brain is multi-scale by its nature, maybe you also want to create multi-scale simulations. And here, for example, my colleague Wouter, who already talked at the beginning of this module, worked a lot on defining structure for these multi-scale simulations. And today we have different instances on how different tools can work together to exchange data and to create more complex workflows that integrate all these phenomena emerging from the very details of cellular models all the way to the whole brain, or even towards embodied AI or other types of future applications, maybe comparing with the in vitro experiments, or to define brain-machine interface configurations, parameters. So there is a lot to be done, but because eBrains has allowed us to create these horizontal links, it is possible to create the connections between the simulation tools. And now we're going to move a bit towards the analysis and visualization, because of course it's great if you simulate all this dynamics, but then what do you do with the output data, right? Before we move into that, I want to give you a quick example for example, of these connections, of the multi-scale connections. This is a recent paper where there was a connection between Arbor and the virtual brain to create these multi-scale models of epilepsy, and where you have very detailed information being integrated into a model in Arbor to create to define a region in the brain where you want to place your or develop your hypothesis. And this brain region, which here is marked with a star, is then embedded into a whole brain using the virtual brain. And then one can make tests and do in silico studies about the propagation of seizures starting in this region by setting the parameters of the detailed model here, and how this gets propagated to different other regions in the whole brain. So this is just an example of this multi-scale approach that is enabled because of this crosstalk between tools in eBrains. Yes, so as I mentioned, of course, once you get a lot of data, you need to simulate it. But also before you get that data, right? Because sometimes visualization is not only about looking at what was produced, but also creating usable representations of the models themselves. For example, in the case of NeuroScheme, this is a tool that helps you create models using abstractions instead of having to define the cell models with all their details. You create abstract versions of the cells, and then you can export those abstracted constraints into specifications that will be used by other simulators like NEST or Arbor or TBB. And you of course maybe also want to look at the defined structures of the brain. And neurotouch mesh is one of these tools that allows you to visualize all these intricate connections between very detailed um, um, structures of the brain. And B-Simple is more the element that allows you to understand the dynamics. And I hope this, oh, well, it works. It doesn't work really great. There is a little bit of, I think because of my, the rendering from my tool. But basically, this is a short video that shows the propagation of a wave of activity from one cell into a model of the hippocampus that was produced by one of our colleagues in CNR, who has been working on these models for a very long time. And these visualizations, of course, allow you to understand if actually the model makes sense and if it actually is reaching this whole, this more overarching activity or dynamics that you would expect from the model itself. So these very funny green dots that are everywhere here. Sorry for the rendering problems, but we will share the slides and then you will be able to see this nice video in its full beauty. Yes, and we of course need to analyze the output data. So EBRAINS has many different tools to do that. Elephant is one of them. Elephant is a tool that allows you to analyze electrophysiological data or synthetic data that has been produced from simulations like, for example, from NEST or Arbor. So they are really well aligned and compatible with each other. Then we also have some other validation and test libraries, for example, network unit, morpho unit, hyperunit, and serve unit. And they allow you to run some structured validation tests on your data. They work on different, at the different levels of abstraction, and they provide you then with a set of scores that you can use to say, okay, my data is actually fitting in the right area, or I'm just producing some weird data that has no biological realism at all. So something is wrong. And this is really very important when you do your research. Of course, we don't want to jump to assumptions based on data that has not been thoroughly validated. We also have NEO. NEO is a nice, not only set of ways to load and annotate electrophysiological data and imaging data. It's basically standard, and it provides the structure of the data definition that other tools use, for example, Elephant, which we mentioned before. And having an alignment in how the data should look like and what metadata should be available about this data is critical, because otherwise other tools will not understand what to do with this data. So NEO provides a leveraging basis of information that can be used to work more coherently across different tools. And the last analysis, no, the almost last, this is previous to last. One of the other analysis tools, this is actually a pipeline that we have, is this CoverWAP tool that allows you to analyze brainwave data, brain state data, and how there can be different transition stages, and analyze emergence of waves and other types of complex dynamics that result on these more coarser grain recordings of data. So you can identify or detect waves, you can detect blocks, you can also characterize different features of the data that you are analyzing. So it's a very nice tool to work with this type of data at a different scale. Yeah, the Quint workflow is also one of the workflows that is being heavily developed in the latest project in EBRAINS 2.0. And Quint allows you to create this full pipeline of analysis from this spatial analysis of features in histological images, or also other types of imaging modalities of the brain, and to extract features from them, especially creating or quantifying, for example, numbers of cells of specific types, and automatically analyzing these structures. And this is super useful because this is a connection between the experimental neuroimaging and that can be fed into the modeling tools that we saw before. It has different tools. It's formed also by different sub-tools. For example, the QuickNI, which is used for the registration of the images, and Elastic, which uses machine learning to do the image segmentation and extract labels from that data. So this can be used later for these quantification reports that are produced. And Elastic, actually, you can also use it independently with your own images and run on the supercomputer to create this segmentation. The last analysis tool that I wanted to show you today is FRITZ, which has to do with the analysis, again, of neurophysiological data. This can be, of course, also synthetic data, but it deals with a different set of metrics, and it has more to do with the measures of information transfer, information processing within these data sets. And this is, of course, very useful when you want to do machine learning, or when you're interested in analyzing the complexity of brain dynamics, emergent behavior, chaotic behavior, and other features that are frequent in different states of cognition. And for example, changing states between sleep and awake, and other hallmarks that are important to identify brain neurodegenerative diseases. So this tool becomes a great asset. You don't have to rewrite all these metrics. You can reuse the tool and take the best out of it. Okay, so we actually reached the end of that. A very long introduction to just a few tools. As you can imagine, there are quite many others. So questions. I see Omar shared a question. He says, I noticed the neuromorphic hardware is mentioned multiple times, but I am not aware what is that term. Okay, we are actually gonna dive into that in a few minutes. This is exactly the topic of the next session. So I hope this will be clarified in a minute. But basically, neuromorphic hardware is a set of new technologies that aim at getting inspiration on how the brain works and creating new hardware and computing approaches to to solve different problems. This type of hardware then becomes a possibility, or takes a room with other types of specialized accelerators, computing accelerators, but in a more specific way. So most of the neuromorphic hardware tools work with spiking neural networks, but they are great to exploit the features, some of the features that we see in the brain, to make compute a lot more efficient, especially in terms of energy. But we will see that in more detail in just a bit. Other questions? Okay, if not, then I take the time to very quickly give you a tour to the different, so just very few tools, so you get a better glance into them. If you go to EBRAINS in the data tools and services and you go to modeling and simulation, you will land here where you have all the brain simulation tools. If you go to see all the tools, then you will get a long list of many tools that I didn't mention and some of the ones that I mentioned. So there is really a large amount of these tools. Today I want to maybe show you just a few. For example, we discussed these cellular level workflows and use cases, and here there are many different modalities. We already saw this. So you have analysis of traces, single cell modelings, analysis of morphologies, a single cell experiments, and you also have these small circuit in silico experiments. I want to look quickly together with you to this rat hippocampus model, which automatically launches this view of the rat hippocampus. And yeah, where you can, for example, yeah, I'm too far away, but there is a cell number 1 is here in the middle, if you can see it. So I just added here, but maybe you can also add cell number 2. And these are the identifiers of the cell in the model, right? So these are just a few of them. And then you can select different cells from them, and you can proceed with the simulation configuration. And here we have the 2 cells. Here's one, and here's the other. And you can record from here. I'm recording from the soma in the cell 1, and maybe I can also record from this other cell here. If my hand works. Okay, so we have some recording and some stimuli already provided to the cell, in this case, this single cell, and you can run a short simulation of how this cell behaves to some stimuli inside of this network model, and you can get the voltage trace of the cell embedded in the network, right? So it is a very nice in silico experimentation environment where you can, of course, already make use of these very nice existing models and explore a little bit what is possible without really having to code, program, or download anything, because it is all available via the EBRAINS services. Another tool that we discussed was Nest Desktop. And here, for example, you can have this graphic user interface with, here are some examples already provided where you have some like spike activity. Let me see if this is configured in such a way. Okay, because my backend is not running, but I didn't set it up. So, but in theory, you can just set up your simulation. You can add other types of a Poisson generator, change the the type of cell that you're working with. You can add a spike recorder or a multimeter or voltmeter. So for those who are already a little bit acquainted with Nest, this of course also provides you with the Python code that you could also just copy and execute it locally in your laptop and just visualize the results. And it is a very nice way to get started with some very easily with a graphic interface to do some small tests and simulations with Nest. If we go to the full brain, and there are also several services provided by the virtual brain that we discussed before. You can launch the TBB service that it already gives you access to a cloud deployment of TBB. And here, of course, I'm already logged in with my EBRAINS account, so it recognizes me, and you can define a new simulation, execute some simulations on the back end without having to install anything, and using the graphic interface from TBB. You can also connect to the multi-level atlas, as you see. So everything, you see how it's crossing and feeding into each other. And this then brings you a great playground for you to start exploring. Usually, more advanced users do not use the GUI anymore because they want to deal with all the details that are enabled through Python programmatically. But to get started, this is a great way to start setting up your simulations, to explore the data, and to get an overview on how TBB works and how it can be useful for your experiments. Yes, so that was everything for this section. So I think that we can have 5 minutes to stretch a little bit, but before we go, I want to put the next set of questions for the treasure hunt. How are you doing with the treasure hunt? Are you finding actually the words? Is it starting to sound like something? Are you okay? Good, good. I'm happy that you are finding them. Don't ask ChatGPT to get to come out with all your responses, okay? Take the time to go through all the different sections. Okay. 5-minute break to stretch, get some water, get some energy, and then come back to talk about high-performance computing, neuromorphic computing, and AI. Okay, thank you very much. In progress. Okay, everybody, we're back then to the next section that has to do with high-performance computing, neuromorphic hardware, and some sprinkles of machine learning and AI. And let's get started with the neuromorphic hardware, actually. So we had the question of what is neuromorphic hardware? And yes, as we mentioned before, neuromorphic hardware tries to abstract features of how the brain works to create new computational architectures. In the case of EBRAINS, we have 2 contributors to the neuromorphic hardware infrastructure. One of them is a Spinnaker. Spinnaker is a digital multi-core chip that uses the ARM architecture. These chips have an optimized routing communication strategy that allows to have very fast communication of events between different elements being executed in the hardware. This is especially interesting for spiking neural networks because, as you can imagine, when you have a network of spiking neurons, one of the most important features that is used to transfer information between the neurons is the spike and the emergence of this event detected as a spike. And so these events need then to be communicated to all the receiving neurons, so the postsynaptic neurons. And sometimes this can be very difficult to do because the more dense the connectivity is, the more communication there has to be between different processing elements. And sometimes this can lead to a bottleneck. However, this hardware is particularly designed to be more efficient in that sense. And in some models, it can achieve real-time operation, which means that any execution of or simulation of one biological second takes exactly one biological compute time, right? So as compute time simulation. And this is very important because the more complex the models are, the more difficult and intricate are the questions to be answered. Usually, the more time it takes to simulate these models. And if we need several hundred minutes or even days to simulate a few seconds of biological dynamics of the cells, then it becomes impossible to answer some of the questions that we want to address. Here in this picture, we can see the Spinnaker 1 system and the Spinnaker system. The Spinnaker 1 system is currently hosted at the University of Manchester, and the Spinnaker 2 system is located in the University of Dresden, or in the deployed through SpinCloud, which is a spin-off from the University of Dresden. And it is both of these systems can be accessed using or getting authorization via the EBRAINS infrastructure. We also have another neuromorphic hardware that is called BrainScales, and BrainScales has a different approach to neuromorphic computing in the sense that it has a mixed nature. Some parts of it are analog. This means analog circuitry, and they have a digital interfacing so that it can also work together with other computing resources. But the way it works is that it exploits the inherent features of the transistors and the circuitry that is in this analog network to emulate instead of simulate the dynamics of the cell membrane, and by abstracting the cell as an electrical circuit. And this approach can lead to hyperacceleration of the emulation and simulation processes, because you are really leveraging the natural features of the hardware itself. This hardware is developed in the University of Heidelberg, and here below is a nice video, but there are many resources available in the EBRAINS website where you can see videos about the installation, the operations, the usability. And if you are interested in the neuromorphic hardware field, there is a very nice conference that takes place every year, the NICE conference. It's really called NICE, and there is a forum to exchange and discuss many of the developments in the area of neuromorphic hardware. So you can follow on that if you are interested to know more. I took this image from a recent paper from also some of the colleagues that developed the Spinnaker system, which shows the development of neuromorphic systems in time, as well as the number of neurons that they can simulate, emulate. Some of them here depicted are academically driven neuromorphic systems like Spinnaker and brain scales. And here there are also more commercial systems like TrueNord and Loihi, which are driven by industry. And as you can see, the neuromorphic field is really ramping up and increasing the number of neurons that you can simulate or emulate, depending on the technology that you are using. So it is a field which has a lot of attention at the moment, and which also provides a totally new way of thinking about how to do compute, because so far we have been using them mostly to simulate spiking networks or abstract neural networks, artificial ones. But the applications for this hardware might be far more broadly reaching in many other different fields of science. It just requires that we think a little bit different, and it is a little bit similar to at the end of the 90s when GPUs were started to become more general purpose. And I think in this sense, accelerators like these neuromorphic chips will become more broadly applicable to different areas. As we mentioned, they are also aiming at reproducing different features of the brain. And this image is also from that nice Nature paper from the colleagues in that some of the colleagues who developed Spinnaker. And here there is a diagram of some of these features that are maturing slowly into the hardware infrastructure. The connectivity patterns, if they are aware of their own resources or not, the scalability of these systems. It is not said that these chips can be just normally scaled up, so you can put more neurons in them indefinitely. There are different constraints, and of course the brain also has its own constraints to set how many neurons you can fit in your skull. But with the neuromorphic hardware we have a different set of requirements and restrictions that have to do with the physical substrates where they are implemented. Then we have this asynchronous communication, this event-based approach to communication, which is really unique, I think, in the neuromorphic hardware community, and that makes us rethink our previous algorithms where things kind of work sequentially, or we are used to think that things work sequentially, but instead here many things can be asynchronously be happening together. And it is an interesting exercise to rethink how we do compute and what actually computing means. There are other features related to the hierarchy of the compute, the heterogeneity of the input-output devices, so the sensors and the actuators. And of course, one of the real challenges is plasticity, neural plasticity, right? Achieving the reconfiguration of the structure of the networks, which in hardware might be very complex because we don't have this living system that can adapt and create new pieces of itself and physically connect to a new neuron when it needs to. when it learns something new, or strengthen a connection when two neurons need to work together to solve a problem. So this poses many different challenges to the development of neuromorphic, but with motivated young researchers, I think this field has a lot of future, not only for the area of compute, but also for medical applications and artificial intelligence. And I will show you some examples, because especially for artificial intelligence and machine learning, neuromorphic computing has been a real working platform so far. And I want to touch this AI and machine learning point because EBRAINS is a place where these fields interact quite a bit. It's not only developing AI methods that are useful for neuroscience, like we saw in Elastic, right? So methods that can be used to do the segmentation of images, or using machine learning tools that are biologically feasible and are used to explore or optimize models. It's also the other way around, how neuroscience contributes to the future development of AI and what it means to extract knowledge from how the brain learns and operates, and what happens when it rests and when it consolidates information. What is the relationship between the structure of the brain and its function and the development of the brain as time goes by, and how this can be useful for developing new technologies. So this is really a meeting point for all of these discussions. In EBRAINS, there are tools, for example, like Learning to Learn, which is here on the left side, which is a tool that is mostly a machine learning tool for neuroscience. It's a tool for doing optimizations, parameter fitting on high performance computing infrastructure. On the right hand, we have examples of connecting brain models to physical embodiment experiments. In this case, this is a rat that has been connected to a brain model using Nest, and then you have a gazebo that is serving as the physical simulation for the environment, and then you can have a task or something going around this setup where you can expect the brain model to learn, to ingest inputs from the environment, to produce the right outputs into the environment, to modify the environment, and so on and so forth. And if you're interested in this, I invite you to look into these nice papers. There has, of course, been a lot of discussion about how we can utilize the brain features to do image processing and segmentation and to identify patterns and features in natural images. And some colleagues have really put a lot of attention into developing complex brain-like models that are interesting or reflecting, interesting in the sense that they reflect the way how visual input is processed and how the outputs of these models can be used for more efficient, more generalized AI. And of course, then there is a nice connection between the neuromorphic hardware and AI. So here is an example of a tool that is used to connect PyTorch, the very popular tool for artificial neural networks, with the neuromorphic hardware. In this case, the the brain skill system to produce an environment where you can do learning with the neuromorphic hardware in the loop, and then you can train these spiking neural networks on a specific task that you want to achieve. But of course, just before I move forward, this is a very interdisciplinary approach, right? You will have to combine neuroscience insight with the engineering to produce these chips and the computational computer science, computational neuroscience approaches to make sense of all of these things moving together. And so these are some of the examples on how neuromorphic hardware is moving forward in the field. And I hope that you feel motivated to look more into them and to request access to them with your EBRAINS accounts so you can start testing the possibilities if this is useful for your use cases. Now I'm going to move forward to high-performance computing. And I mentioned in the beginning that the Human Brain Project, during its 10 years of existence, or a little bit more, had this tight collaboration with the Phoenix Research Infrastructure. The Phoenix Research Infrastructure was an effort of these different high-performance computing centers in Europe to provide a federated infrastructure for computing. Today, Phoenix is more oriented to cloud resources, but in its beginning, it had also provided high-performance computing resources. And the idea was that users, not only from EBRAINS, actually, Phoenix is available to users of many different disciplines, but because EBRAINS was the first community and the early adopters, then we had the privilege of testing all of its features first. We could get access to platform services and execute, for example, the collaboratory and the different platforms and get some generic platform features already integrated with them. Within the new project, the new version of EBRAINS 2.0, users from EBRAINS can also get still access to high-performance computing resources in English and also partially in Chineka. And why is high-performance computing important? Well, it provides a way to access storage for large amounts of data. So if you have very big data sets or you produce very large simulations, of course, it is not easy to just store them in your laptop because then also they wouldn't be useful for the rest. So HPC centers have provided this infrastructure for storing data, and that is also very closely connected to large computational resources and visualization resources. The centers have also provided cloud infrastructure, which is useful to deploy the services that you saw. So, for example, the knowledge graph, the atlas, all these, the TBB tools, the simulation tools, the modeling tools, they are all deployed on this cloud infrastructure that make it easy for you to interact with EBRAINS. And as well as all the platform, I don't know if you recall that image that we saw at the very beginning of the architecture, those platform services, of course, also need all this cloud infrastructure to be able to monitor and connect and test and make sure that the tools are deployed correctly throughout the infrastructure itself. And of course, high-performance computing itself gives a new avenue to explore the brain. We can create simulations of models that were not possible to simulate before, including plasticity and modeling brain development and stimulation. And neurodegenerative diseases. All of these things really need a lot of computing power. But not only that, we can also fit the models to data and create workflows to validate those models. So this is becoming an infrastructure that can be really helpful for you to do your research. In general, users can deploy workflows on the different HPC sites that were connected to the HBP using Unicore. Also to some of the neuromorphic hardware sites. So this is a unifying element. And the EBRAINS, your EBRAINS account is really, again, the key to make sure that all of these infrastructure resources are available to you. Yeah, EBRAINS is actually building a new scientific community of brain research around HPC. And we want to fit these services to the requirements of the community. This includes integrating expertise from different fields and cooperating with different research groups, but also supporting critical examples and showcases so that the community can get more motivated into using the infrastructure. And in the future, of course, we would like to have a better, a more homogeneous way to deploy infrastructure elements. We're working hard on that. So colleagues, for example, in Athens and in Heidelberg are working very hard for the EBRAINS software distribution, which allows to have a homogeneous, unique distribution of all the software tools into different platforms. Also moving forward to containerization to create even more easy deployment of these tools. And of course, moving forward, this personal space that you can log into in your EBRAINS website, well, it should also keep track of the resources that you have assigned to you in the future and where you have some available computing time, for example, available storage, but this still needs a little bit more development. One important thing for high performance computing is our integration to EuroHPC. EuroHPC is a European initiative that connects all the bigger computing centers in Europe and provides access to computing resources, cloud resources, cloud and HPC resources, but especially for the HPC part, and especially looking into doing benchmarks or developing AI related tasks. EuroHPC is critical and a very important initiative with which EBRAINS is looking to collaborate to also deploy these tools that you have seen in there, so you can use them right away when you get access into these systems. I just wanted to give you a quick example of one of these applications of high performance computing in neuroscience. This is a paper where we did a tremendous amount of parameter optimization for a clinical application. In this case, we had a model of deep brain stimulation that consisted on having a representation of the subthalamic nucleus and the globus pallidus externus in NEST. And then we were able to simulate on healthy synchronization and stimulation protocols. And this was basically to study the effects of this deep brain stimulation that is frequently used to treat Parkinson's disease. The model in the past used to consider just synaptic plasticity, and then we made it even more complex by adding structural plasticity into the mix, which required a lot of computing power, because now we were not only talking about changing the strength of connections between neurons in this model, but actually rewiring the network. And the hypothesis was that this stimulation was actually triggering some rewiring in the network that allowed it to progressively react better to stimulation. And in this sense, before this experiment, it was not possible to reproduce the clinical observations that when you did this stimulation repeatedly throughout time, the desynchronization process became faster. And so here we have an example of a simulation. You see, you have the two populations here in red and blue, and then this gray region of 10 minutes where the stimulation was being provided to the model. And when the structural plasticity was enabled, and during this period of rest, it was possible to rewire the network so that in the next sessions, less stimulation was required to achieve the desynchronization. This took hundreds of thousands of core hours to do, because just the amount of parameters that were required to observe and tune to find the right regimes and to exploit the features of the network in its more biological realism were really complicated. So this is just an example how high performance computing can be useful for working towards clinical applications. And my last point here is about how do I get access to the high performance computing infrastructure in EBRAINS? Right? So some of you maybe are wondering, can I get access? You don't get automatically access to it with your EBRAINS account, but if you have your EBRAINS account, you can, for example, once you have gotten resources in, let's say in ULISH, you can deploy jobs directly on the system through the collab. And we will talk more about the collaboratory in a bit, so in the next session. But before that, I want to say that there is, at the moment, a limited amount of resources that can be accessed at the JSC. You have to fill a form, and I will actually switch my view so you can see this. Let's see if I manage to find the right window. Oh, was so nice to put it on top. Perfect. So in the collaboratory, there's some information about how to apply to these resources. These are the resources that are available through EBRAINS 2.0. So basically, you have to fill a template and send that template to the Brace infrastructure email address. This request then will get evaluated on the technical side, on the scientific side, and then you would get access to the resources if everything is correct or everything is suitable. And there are different other ways to access HPC resources. Each of the different centers that are involved in EBRAINS also provide regular national calls to their hardware. And there is also the Euro HPC codes that I mentioned before, where you can get access to systems also around Europe. One important thing is that if you want to apply for these resources and you don't know how to fill these forms, or you have questions about what to put where, or which tool should I say I will be using, you can always contact us via the support contact form, and we will help you then work out what is the best way to put together your application. And maybe I very quickly also show you what that template looks like, so you get an idea of what you have to provide. So a second. I'll give you there. Okay, so you basically have to provide some information. Here, then a small summary about your project. Why are you? Do you want to? What are you doing? What is your use case, and why do you want these resources? Then you have to provide a small preliminary work. Define what is your methodology. What are your goals? Why are you using the tools that you are using, and how you're putting them together to make sure that you achieve your scientific goal. And then you have to provide some short resource management and work plan. So how are you going to use these resources, right? If we give you 1,000,000 core hours on the system, what will you do with them? Well, maybe your simulations, you want to do, I don't know, 1,000 simulations, and each simulation requires you to use one node, and each node in use has 128 cores. So you start to multiply and it takes me 1 hour to execute each simulation. So I have 128 core hours per execution step, and you start to gather all your requirements in terms of compute. Sometimes this is very difficult to know, especially when you're beginning to do the simulations. So this is why we provide you support to benchmark your applications, to test your tools, and also to give you guidance on what to put in there. You need also to provide a data management plan, especially if you what amount of data you want to put in and out of the systems. Then some more details on the technical implementation. Here is all the details and table with the number of jobs and the type of jobs and the duration. Do I need CPUs? Do I need GPUs? How long will it take? How much storage do I need? Etc. etc. Then a few questions. Have you used this software already on a supercomputer? Do you need onboarding? Are you using personal data? Most of the HPC centers do not allow you to process personal data as such. There are some circumstances in which pseudonymized personal data can be processed if the pseudonymization is done depending or based on specific guidelines. So it is important that you always ask what is possible and what not. And then our data protection officer will take a look and say, yeah, okay, that is possible, or no, unfortunately, it is not possible to process this type of data in our infrastructure. And the main thing is that high-performance computing centers provide services to many researchers and to also industry partners. They are not isolated infrastructure elements. So there is an accessibility layer that makes it for a little bit more complicated to ensure that sensitive data is processed in a way that it matches the data protection regulations. So we have to be very careful with that. Yeah, in the end, then you are just asked to say how many node hours you would like in CPUs and in GPUs and where, if it's Chineca or JSC at the moment. These are the two centers that are offering services. Then how do you want it to, how will you disseminate this? And some references. So as you see, it's a comprehensive document where you have to explain your research and let's say justify the access to the resources. But once you have put this together, which is also a good exercise for you, because it makes you think about all your needs, all your requirements in a more structured manner, then you can submit this and get access to the computing infrastructure. This is how the template looks for these EBRAINS resources, but for the national calls, these templates are a little bit more elaborated. In general, they have more or less the same points, or they cover more or less the same points, but they require far more detail, and you need to provide more evidence on the scalability of your methods and the way you will use the resources. Because they are very competitive calls to these resources. Okay, questions? Okay, I see no questions. Then here is the new set of hints for the treasure hunt. And you can find them in the chat, but here as well. And okay, with this, we are finished with these two sections of the module. We are missing one section to discuss about collaboration and one final question and answer session with a bit of discussion. I would suggest that we go early into the coffee break, take a bit more time to relax and maybe look for any missing answers for that treasure hunt. If you feel like exploring some of the tools that we discussed before and come up with questions in the meantime, please collect them and we will get to them in the question and answer session. And also feel free to continue adding your thoughts to the mural so you can keep track of anything that resonates with the way you want to address your use cases or questions within EBRAINS. Okay, so if there are no other questions, let's take a bit of a longer coffee break. We see each other at 3:30 back for the collaboration section of the module. Okay, thank you everybody. And now we are heading into actually the last section of the module, which is a very light and I think interesting section as well. It has to do more with how we do science. So let's get started then with this last section. We have three things to talk about here in this section, and I will do a quick overview and then we are gonna go visit these places because these services are better understood when interacting with them. So the first thing that we use to do collaborative research in EBRAINS is the collaboratory. The collaboratory is a shared environment where you can create small collabs, they are called. So they are small spaces which are assigned with a wiki and also some storage space. And you can also connect directly to the lab instance that we have in eBrains. That means that you can connect to Jupyter notebooks that might be of relevance for your work. The collaboratory can be used in many different ways. You can use it to store information that you want to share with other colleagues in a project, or you can use it to access the Jupyter Lab and keep track of your experiments. You can use it to upload data that you need to use, not personal data, because this is not meant to hold personal data, but other types of data that you may want to use and you may want to share with other colleagues. And you can use your eBrains account as well to define different levels of access that people can have to this virtual space. You can use it to do project coordination as well. We used it for that during the Human Brain Project, where we basically collected all related documentation, information about the progress of the project, presentations, and other types of documentation. You will see that the collaboratory also collects a large amount of information about the tools that we have seen throughout the day in this documentation section that you see in the top right menu. And it offers you an environment to exchange and to create these spaces to do your research. I find the collaboratory a wonderful tool. I've used it for years, and you can find many useful examples of applications of the different tools in the collaboratory. And we will take a look at some of them in just a minute when we start diving into the space. But first, let's finish with the overall overview. So that was the collaboratory. The other collaborative space is the community space. The community space is a service where you can join different communities that have some topical interest. Let's say about the brain atlases, or about neuromorphic computer, about consciousness research. And you can also create a profile there. You can let people know about your work, share events, notify people about what you're doing. It has a bit of the format of a forum where you can post notices and exchange with other people in this way. So it is also a different way in which to build a community. Maybe you are interested in driving a new community, then you can send a request through their support mechanism to start a new community, and you can start coordinating this effort as a driving element, in a leadership role, let's say. Or you can just join all the sub-communities that you like to keep track of all the changes and updates in the EBRAINS infrastructure. The final element that I wanted to discuss in this section is education and training, because, well, of course, this is part of the education and training in some sense. So there are many initiatives at the national level and the European level that contribute to generating an educational offer for eBrains. We have a large amount of tutorials, videos, examples, documentation. There have been digital schools offered during the Human Brain Project, which have been recorded and that you can look at also in the forms of videos. As you can also contribute yourself if you are an expert in a specific tool and you want to contribute that there are different mechanisms to, for example, propose a workshop on one of the education-related conferences like the student conference that maybe you saw in the slide before, but we will have the EBRAINS student conference on the 11th of March in Nice. Some of you already are aware of that. But this is another mechanism for interacting with education activities. And it is, it has, of course, also the objective of contributing to the next generation of researchers who should also integrate all these new skills that are being developed within the program in the future. So these are the three platforms. We're going to visit them. So the first thing that I wanted to visit together with you is the collaboratory. As mentioned, for me, for a long time, this was the main working space for EBRAINS. In the collaboratory, you can find so many resources and information about the tools that it's really, really useful, and it is a main working space for doing your research. You can, of course, start by searching words here. For example, you can, of course, write any key value that you would like to find in the wikis. You could also just use one of the existing links here that I highlighted. We already talked about the Quint workflow, so maybe this is an interesting connection to make. So here, for example, the developers of Quint have provided some examples, some online documentation and description about the different tools that are related to the whole pipeline of Quint. Then there is a description and some videos about how to make use of it. This is then a way in which you can create an open page to share this information with, in this case, with potential users. But you could also do something similar if you are doing a project and you want to leave it open. You can have private collaboratories, you can have public collaboratories. You can see the difference here in this part and upper left. And as I mentioned, each collab has a bucket that is where data can be stored. They have the drive where you can, of course, you have to allow and give permission. But here you can upload files of different types, videos, doc files, figures, anything that you would like to share with your groups. And then, of course, you also have the lab that we saw already before. It prompts you to open the lab interface. You can select if to execute the lab at the JSC, at the Juli Supercomputing Center, where we are located, and where you can launch this Jupyter lab interface, or you can also do this in Chineca. And we have this in such a way that there is always a backup for your service. So yeah, you can launch the Jupyter Lab, and then yeah, you get access to the Jupyter Lab, which is also one of the fundamental elements of working and collaboration inside of the EBRAINS infrastructure. I love the fact that the collaboratory is directly connected to the Jupyter Lab, because it gives you total access, like a seamless flexibility between these two elements of documentation, wiki style storage of data with the active usage of the tools, testing and implementing maybe models, analysis, anything that you may need that is utilizing the EBRAINS infrastructure. When you are in the lab, you can navigate in different areas of the collaboratories that are available. And yeah, you just need to be careful when you navigate here. You can get lost very quickly. So make sure that you know well where you want to go. There is one entry here for each collab that has been created. So if you see there are really hundreds of collaboratories that have been made. Some of them are public, some of them are private. If they are public, you can enter and take a look at their lab examples, like the example that we saw with the live paper before in some of the earlier session. But if this is public, it will tell you that you don't have permissions to access. And yeah, then you can, of course, also go to your more personal space. If you go to my libraries, and here, well, I have a bunch of things because I work a lot with different things and examples about connections to the supercomputers, connections to different tools and services. But here, for example, you can create these connections to launch jobs on the supercomputer using Unicore. And we were creating some tutorials for that. You can, of course, create a new file, and you can actually choose a kernel that contains already the latest release of the infrastructure. So it is already tested that, so here some of the tools are already available. If I do import Nest, I don't have to install anything. Nest is already available and I can make use of it directly into my interface. So I have all the tools that are part of the eBrains software distribution are available here. And this makes the interaction really easy, and you can start prompting right away or creating your scripts and saying, okay, what are the tools that are available, and then creating your steps into your Jupyter notebooks that might be of use, grabbing data from the knowledge graph or querying some information about the structure of the brain from the atlas, and then creating a new model in Nest, or submitting a new model to the neuromorphic hardware, which is also possible from this interface. So there is a lot of space here. We will have more dedicated tutorials to the different tools in the following modules. So this will become even more practical for you. But yeah, this is the power of the collaboratory. I feel that it is a very nice intersection, a combination of tools. And beyond the specific collabs, you also have the documentation for the tools, as well as the documentation for the collaborator itself. There are some technical details, and there are some tutorials, for example. This connects directly to the education point. So we will see this in a minute. And then, of course, the support is always there for you. So if in question, then just go there. Okay, we already talked about the lab, so I don't have to explain this independently. But what I would like to do now is go to the eBrains community space. Has anybody already entered the community space? Hands up if you have used the community space. Not yet? Okay, then this is a great introduction to the community space. So when you first visit community.ebrains.eu, you will be prompted to create a profile, actually. And yeah, you can edit your profile. I have just a basic profile, but you can also have a more comprehensive profile, and you can fill many different details. This helps, of course, also create interaction with others who might be interested in working with you, collaborating with you, or discussing with you. Then you also have a way to look which communities are already there. Yeah, there are many nice projects going around on different tools, on different questions. There's about ethics, about artificial intelligence, about the brain atlases, about high performance computing, of course. Yes, so there is a large amount of possibilities to exchange and to be part of this community. So I encourage you to also take a look and see what is going on. We have, for example, the neuromorphic community, and you can have some forums where people share newest papers or updates in the hardware. So it is a place to exchange and a place to network. Of course, besides the community space, we also have our working environment in folder case for EduBrains. But I will not go too much into detail here today. We already discussed this in the introductory session in Module 1. So the final thing that I wanted to talk about is the task points, right? Well, the education and training in general. So if you go to eBrains and you go to this participate section, you will see the different education and training offerings. And here's, for example, the e-library and tutorials, the student community. So if you are an early career researcher and you want to join the student community, there are different things that you can do. We have student ambassadors, we have our student representatives, which one of the participants in the EduBrains program is a student representative, actually. So we have different representatives of different aspects of the community to make sure that eBrains is actually addressing your concerns, your questions, and your needs as the future of the infrastructure. And we also have the Education Task Force, which is something that we are working on together in different topics, like increasing the visibility of the education offerings, or include collaboration of early career researchers, and to collaborate better horizontally with new programs and grants. For example, EduBrains is one of these lateral collaborations that is very important, in particular to move forward the topics of applying eBrains to the future of brain health. And finally, if you go to the tutorials, you will see that it brings you back to the collaboratory, and here you can find a large amount of a large collection of tutorials for all the different tools and more from which we discussed today. So there is a lot to learn, a lot to see. If you're interested, you will definitely find enough information here. For example, if you want to start with Arbor, here are some tutorials, some small models, and they are all categorized in the level that they are tailored to, and the type that they are. If there is documentation, if there is a video, if it's some other type of material, right? So you can find a lot of things here, and I think that this is basically the closure point for these collaborative spaces. I hope that you find them also engaging, and that you feel motivated to participate actively in all these spaces as part of the EduBrains program, and also in your course becoming the power users of eBrains. Okay, so any questions? Ellen had a question about how you can access. Okay, but the information, yes, will continue to be shared in the folder case website for the participants who are joining outside of the formal EduBrains program, but you will still be able to join online to some of the modules. Okay, I see no questions. So we have arrived to the last section, that is the questions and answers. But I want to start with giving you the last 5 questions for the treasure hunt. Otherwise, you will not be able to find out what was the secret message. Here are the questions. And now the race begins. The first one to raise your hand with the answer will have the chance to tell us what you want to do in eBrains, what's your use case, and we will try to find out which are the right tools and the right approach to address your use case. So, run, run, run! So, when you have collected all the words that go in the brackets, you need to put them in order, and then take the first letter of each of these words and to give me the message that they say. Is there one that is especially difficult? I also tried to almost say all of them during my presentation. So if you were paying lots and lots and lots of attention, maybe you caught all of them. Except for maybe 2 or 3, but most of them were there. Somebody wants to use a jolly to find a word that you can't figure out? Or do you want that we go through all of them together? Yes, Maria, you got it. In this case, you are the future of brain research. Indeed. We are the future of brain research was the answer. So, Maria, do you want to open your mic and tell us a bit about what you want to do in eBrains?
Sure. Hi. Hello, everyone.
So,
My name is Maria, and I'm doing a PhD in biomedical engineering, and more specifically, I'm studying how to detect early Parkinson's disease measuring eye movement. And so it's a little bit more on the behavioral neuroscience part of things, not inside of the brain, but how things happening in the brain actually manifest themselves via whatever the body is doing. And so the part that I was most interested in and that caught my attention, and actually probably after this I will be clicking around and figuring out how it works, was the brain stimulator, and specifically when you were talking about the deep brain stimulation simulations and how that works. While it's not exactly the core of my research, I actually really do think it'll make my whole thesis much more robust because I would actually understand the process behind it, which I have a relatively shallow understanding of. And so that's a little bit what I want to explore. And so I'm maybe a little bit more of a beginner in these topics. So that's it.
Excellent. Thank you very much for sharing, Maria. I think that is a very nice project, and hopefully you will be able to make use of EBRAINS to also help you in this excellent endeavor of trying to understand better the onset of Parkinson's disease, which is so difficult to address and which affects so many people. So one of my recommendations is, yes, the virtual brain could be a great tool to understand the whole brain dynamics. You could also work with connecting the virtual brain with more detailed models, like the model that I mentioned before in that presentation, because most likely this type of eye movement is then related to some adverse synchronization. I don't know too much about this, but I know that abnormal synchronization is definitely a hallmark of the disease. And if you managed to maybe even collaborate with some colleagues who are working more on the definition of the detailed models of how these small networks get over synchronized with time, then you could create some experimental in silico experimental features where you could connect these different levels of eye movement to some emergent states of this brain dynamics, and then you could try to connect those with your experimental observations or your clinical observations, and you could try to find which like what are the model setups that reflect the progression of the disease. So how it starts with very early hallmarks of the eye movement and how it moves forward into the disease. So you could create a full time span workflow to try to connect and create this hypothesis between the computational side and the clinical and behavioral type of the research. Sounds wonderful. Very excited.
Oh, thank you. Also, the way you reworded it gave me more ideas. So thank you.
Very good. Great. Great that it was helpful. Anybody else would like to ask a question or share your use case and you want to get some ideas on how you could get started with the infrastructure? If not, I don't blame you because we have been here since 9 a.m. and we were probably all a little bit tired. We had a lot to do and this treasure hunt didn't help. But I hope you had a little bit of fun during this module. I thank you all for your time, for your engagement and participation. I look forward to meeting the core members of the EduBrains program in person for module number 3, and hopefully other colleagues who who joined that are not formally registered in the EduBrains program can also join online for some of those sessions. I encourage you to continue looking into all these tools, into the ecosystem, how it works, and if you have questions, use folder case and other mechanisms to exchange, to collaborate, to try to answer those questions. Like this, there is like a month and a half until we meet again for the next module, so you have some time to elaborate those ideas a little bit further. And I will create an archived version of the mural where we can also collect some of your feedback and ideas and information about what you want to do and what are your expectations about the EBRAINS infrastructure. Okay, and if we don't have any other open points, with this I would like to close module number 2 and wish you a very nice rest of your day, a wonderful weekend, and yeah, see you all very soon in English.